Hello and welcome to this video. I'm going to discuss the EPS board design for the CubeSat. So I'm, let's say, 99% done with the design of this EPS. It's not okay. It's pretty basic, but it's not very advanced either. Well, that's the same thing, but it's not too basic because I've tried to add a lot of features that I think and I am certain that will be useful for the CubeSat. So basically, it's divided into three parts. Yeah. So the first part is the input, power input, or the voltage and current input. And then there is the data acquisition system, or the modules that will help with acquiring the data of the EPS. And then there is the output, or rather the supply to the other consumers or loads on the CubeSat, things like the ODC, COMS, ADCU, etc, etc. Yeah, so I'll try to go as much detailed as possible while keeping the video short. But to start with, this CubeSat, I've designed it such that it can be tested on the bench and outside also. So the input right here is, there are two inputs. There's the 12 volts jack, that's from the wall adapter. So our wall adapter can give me 12 volts at 2 amps here. And then there's a solar input, solar panels. So 12 jack is just 12 volts in with DC jack. These are miscellaneous components. For example, this is a jumper or toggle jumper that can enable or disable that. 12 volts in. Inhibit switch, this is just basically a single pole double throw switch with a normally closed and normally open connections that you can connect at this point. This is a part of the standard description that says you must have at least 2 inhibit switches. There are some others, but I'll show you where they are at this point. We just have this one inhibit switch. So 12 volts in, LED obviously for just indication, reverse protection using a P MOSFET, and the next thing is, at this point, this LED will show you whether the inhibit switch is on or off. And then we have a 12 volt jack EPS net here, right? So I have labeled that remove before flight is connected at this point at the inhibit switch. But I'll discuss the RBF, or that's the remove before flight switch, later. Right, so this 12 volt jack, where does it go? It comes right here. So this net is connected to this, right? Okay, that's the first input. The second input are the solar panels, right? So this is the solar panel part. So I've decided to put the panels in on only two sides. Okay, considering it's 3 axes, X, Y, Z, I've decided to put the solar panels in two, or rather on 2 axes, the Z and the Z or Z and the X axis. So basically the Z axis has the positive and the negative side, right? So if you think about it, let me see whether I can illustrate that with paint. If you think about it, if you have a solar, if you have like let me use a better surface. If you have a CubeSat like this, like that. So I want to show you the placement of the solar panels. So let's say this and this and then there is that. So the point of origin is somewhere here, right at the center here, not at the center, at one of the corners, assuming, right? So if we take this as x, this is as z, this is y, this will be positive z pointing this direction, then this side will be negative z, negative z. This is positive x, and then this other side will be what? Negative, rather, minus x, right? Okay, so if now I come to my schematic here and you realize that I have positive z1, positive z is right here. So positive z is this face right here. You can see that. Now, there are two ways I'm thinking about this. Thinking about the like assembly. When I was sourcing for some solar panels on Alibaba, I found that I can get one panel that is 90 by 90 millimeters. Considering this CubeSat is 100 millimeters by 100 millimeters, a 1U, 90 by 90 will basically fit somewhere around here with an allowance of at most 1 millimeter, 1 centimeter on all the sides, right? So it means that you can fit one panel. If I buy the 90 by 90 ones, I can fit one panel on one side. Okay, sorry. So yeah, so you can fit one panel. Now, other panels that I found were like half of that. Half of the face, which means I can fit two panels. I can buy two panels. So this is entirely a logistic and component sourcing issue. But my hardware should be able to take care of all those two configurations. So if you think about it, if you have this configuration of having two panels on each face, it means you have two panels on the positive z, two panels on the negative z, two on the positive x, and two on the negative x. So the hardware or the design is able to handle two panels on positive x, z, two panels on positive or negative z, two on positive x and two on negative x. That is if I go with this design. If I go now with the other design that has a single panel like that, 90 by 90, the only thing I need to do on the board or on the CubeSat hardware itself is just remove this toggle pin here. It's called enable two panels Z positive, right? It's just that's what this name means. En to PZ positive. So basically, if you toggle it on, it will enable two panels. If you remove it, you can connect one singular panel, and then it will work, as well. So one singular panel on positive and negative Z, one on positive and negative X, and then of course you have this reverse protection Schottky diode that drop at most 0.25 volts. Those solar panels have very low efficiency, considering their small size also. So Schottky diodes are the best. So what happens after you connect those panels? Assuming you have all these panels connected, I think I've labeled here that set headers if you're using multi-panels. Okay, so all these panels are summed. You bring them to the Z. That voltage is summed, and for the X as well, it's summed to the X panels net. So at this point here, you have a voltage level from all the solar panels. At this point, you have a voltage level from the solar panels on the Z, right? Now, one thing, like I've said, is that solar panels are very low efficiency. So sometimes you'll get if there's low sunlight, not really low sunlight because this thing is in space. But if the orientation is not up to speed or up to maximum, you'll get values of 2.5 volts or 3 volts or something like that, but that's not enough for the usage of your CubeSat. So the next thing that I do is I boost that voltage using this solar boost converter. So I take these two voltages, I sum them, I combine them. The reason I've used 0 ohm resistors is just to separate the nets, because you can't connect this net and that net without placing a short symbol. You'll short those two. Ideally you can in normal, like physically, but considering the software you are using to design, they'll just give you a DRC warning. So 0 ohm is just a way of reducing, as a way of shorting those two nets without introducing any voltage drops, right? So you take those two, you sum them up, you pass them into this TPS 6150 solar boost converter. Is just basically a boost converter, but I've used it for the solar. Takes that, boost it up to 5 volts, so it's a solid 5 volt output with accompanying accessory capacitors also. Then there's the enable pin. Enable pin is used to activate this boost converter. So I have put a RC circuit here, so that anytime the solar panel is on, there's a short delay basically before the boost converter is enabled. Once it's enabled, it is able to take whatever voltage you have collected from the solar panels and give you a 5 volts. So this 5 volts is now an input to this enable, source select button. So we have two inputs, 12 volts and 5 volts from the solar panels. So you can choose which one you want to use. So let's assume that we are selecting the 12 volts, for example, input. So that 12 volts goes to now this BQ25703 V bus. Right, so that's about the input side. Now, the data acquisition and control is now the BQ25703 IC, which is basically a back boost charge controller IC here, right? This one. So this is, I would say, is like the one of the biggest ICs, or the most significant ICs on this PCB, on this design, because it's responsible for power management or power channel management. Now, you can't have solar without a battery in most designs, right? So we have a 7.4 battery to S2P pack, right, that is able to provide 7.4 volts. Now, when you connect a voltage source in, you should be able to charge the battery, and you should be able to supply the load, right? Now, how do you select which source is used to supply the load? So this is what this chip does, the IC does. It is able to charge the battery, right? But it is able also to supply the load with the strongest source. So if I have a 12 volts DC jack here, two amps, that's powerful, right? I only want to charge the battery but supply the load with 12 volts battery at 12 volts jack, right? So this IC will help me to choose which one I want, right? And it has the ability to, you can basically configure it to configure the charging voltage for the battery. I think a maximum of up to 8.4 volts, if I'm not wrong. From the data sheet, 8400 millivolts. Yep. Yep. So that's that. Accompanying circuitry and a couple of MOSFETs, as you can see. So this net is the input net, and then input comes right here from either the solar or the 12 volts. This IC does its job. It gives us two things. Number one, it gives us an output to the battery, and an output that I'm calling VC's RBF. So what is VC's RBF? VC's RBF is connected to the remove before flight switch, right? This is basically is like if you have seen the robots that there are some small robots, wheeled robots that have the limit switches. So this is an example of a limit switch, right? But basically there's a pin. It's like a grenade. It works like a grenade. There's a pin here on the structure of the CubeSat. So you have something. Let me choose a color here. You have, let's say you have a pin that goes all the way through. It can go through or somewhere within the CubeSat, somewhere there. And then it has like a label, like remove before flight, right? So this is oops, what I do? This is remove. If they are usually red and very conspicuous, so that is that. And then now this is what you pull out of the CubeSat when you are setting it into the deployer, right? Before you deploy, you pull this out, so you remove it from the CubeSat structure, and what that does is it will turn on this channel, right? So normally when you're going to deploy, this switch is off, so there's no battery, there's no voltage going to the VCs. And then you remove that pin, that voltage is basically a switch. Yeah, that's what I'm trying to explain here. So VCs is activated once you remove the remove before flight button. So right here we have 12 volts. The battery is being charged. We have 12 volts. You remove that switch or the pin, VCs has 12 volts. So where does these VCs go, right? So VCs go, the next logical thing is to regulate it, right? So we take VCs, regulate it to regulated 5 volts. We take that 5 volts EPS, cascade it down to a linear dropout to AMS 1117 3.3 volts, and that will give us a 3.3 volts EPS that is regulated. So basically you have realized that I've used from 12 to 5 I've used a switch mode power supply, basically because it's high efficiency, low losses, to give me 5 volts EPS. And then in contrast, from 5 volts to 3.3 I've used a linear dropout. There's no need of using an SMPS or a switch mode power supply here for 5 to 3.3, because the drop 5 to 3.3 is around 5 minus 3.3 is around 2 point something. It's a 5 it's a very low drop, right? 2.7 I think voltage, so that LDO can handle that, plus an LED to indicate functioning. It's cascaded that way. And now at this point we have 5 volts and we have 3.3 volts. So the next logical thing is to supply these two voltages to our loads, which are basically the onboard computer, comms, ADC, and the payload. But there is one more thing that we need to do. We rather have implemented what I'm calling the load switches. Load switches are basically a way of sequencing power to the loads. You don't just want to turn on the loads or the power instantly because of something called the inrush currents. For example, if you turn on the comms board so fast and it's using high frequency radio signals or something like that, it will basically pull a lot of current instantly during the start from the regulators, which is as a bad thing. It's a bad design. It might not burn your components, but it's a bad design. So I have implemented some two load switches here that basically they delay the power supply to the load. So this they delay. For example, you feed it with 3.3 volts. You, depending on how you choose these two capacitors, For example, my choice of 1 microfarad and 4.7 nanofarads gave me a rise time of 265 microseconds before the output is activated. So from the moment you feed this to the moment you get 3.3 V load, there's a delay time of 265 microseconds, which is enough for a lot of other components to stabilize. Right, so 5 volts turn on first, which is this one because it has a shorter delay of 91 microseconds. It turns on the OBC. 5 volts is being used by the OBC load. And then where's this 5 volts go? Yeah, let's see. Okay, yeah, so you turn on the OBC first with the 5 volts, and then the 3v3 power rail turns on, because by the time the 3v3 components turn on, the MCU will have stabilized, right? So comms board, which has RF, has its own dedicated load switch for further delay. So I'll show you this in the comms board design, the design change that I've made. But comms board should, based on my design, comms board should turn on the last. Should be the last one to turn on. So these enable pins are basically from the MCU, but I'll discuss that in a few minutes. Good, so from there, we have 3v3 load and 5 volts. Let me confirm something, I think. Okay. Okay, anyway, yep. I'm not sure where this goes. This should go to the connector. Should go to the connector. Yeah, I think I'll fix that. This should go to the connector. Anyway, right. So from there, so you have power supply to the loads, right? The next thing we need to do is now monitor now the voltages. We need data from this. We need data from this whole thing, right? We need to know what voltages we are reading from the solar, from the batteries, from what current, what power, what is our consumption, etc. So the mother of all things is the MCU that will consolidate all that data. It's a basic, cheap, and simple STM-F103C86 MCU. Basically, this thing, I think based on my previous videos, I've explained so much about it so that I don't have to explain all these other supporting circuitry. But basically, 99% of all these components are using I2C. So first of all, this BQ 25703 is using I2C, EPS, SDA, and SCL. You can see that. So basically, that's right there, and it should be here. It's right there. So I can fetch data from the registers of that buck boost converter. And I can also feed this data into like the main bus line, the ISA connector. So this is the same line, but I'm separating it using the 0 ohm resistors again and feeding it into the main bus line. Basically, the reason I'm doing this is to have redundancy. Redundancy. I can read this this IC with this MCU, or I can read this IC with another MCU on board or anything like that, right? Or if there's a bus contention, I can desolder these two resistors and just read the EPS from this IC using this STM32, and then send the STM32 packet to the OBC via these two lines, right? But since it's I2C, I can just chain those two those components together. There's no problem with that. Right, so that's that. We have data from this point. This IC can give you data to do with power consumption, voltage of the input, current of the input, battery voltage, battery current, VCs out, VCs in, etc. A lot of data. I'll show you the data sheet when we are writing the firmware, or rather when we are writing the driver for this chip. All right, so next is how do we monitor the regulator powers, right? So for 3v3, I need to know how much current is being consumed by the 3v3 components of all the CubeSat, or rather on the CubeSat. So I'm using these common and typical INA chips, or rather ICs, family of ICs, to read voltage and current and power. So you realize that this is a small 2 milliohms resistor. Basically, if you pass current through this, you can be able to read voltage. V is equal to IR. This will give me the current being pulled by 3v3 bus components. Similarly, it's just a duplication of these three, are duplication of the first one, but they're really for 5 volts and for the VCs. Yep, and as that different I2C addresses. So all of these are connected to the same bus, which is EPS, SDA, SEL, which is basically this guy here. So I can be able to pull that data from the drivers. Right, so right now I'm discussing the data acquisition systems. Next is I have deployment. Okay, I have a solar power monitor. This is not complete at this point, but there's some connection I need to make on this line. But basically it's the same thing. It will give you the voltage and the current from the solar power, right? From the solar panels, I mean. Okay, so what else is remaining? I have other accessory, no, not accessory really, but very critical components here called the deployment switches, right? Deployment switches are switches that are connected on the, they are connected on the faces of, let me put it here and here. These two switches are called plunger switches. Plunger switches are switches that plunger plunger switches, right? So plunger switches are switches that, for example, once if you press them, they deactivate some components. If you release them, they as long as they're released, they activate the components. So the reason why they are used in the CubeSat is so that the moment you insert this CubeSat into the pod, assuming that there are other CubeSats here, right? If you're using a shared ride share program, so this button will be pressed and this one will be pressed, so your switch will be, your CubeSat will be off, right? Off, will be off. Once you deploy, this is the wall of the deployer. Let's see if I can illustrate that. If this is the wall of the deployer, once you deploy this CubeSat, basically these switches will be not pressed anymore, and they will release and activate your components, right? So when you will be writing the firmware, you'll realize that once you have deployed your CubeSat, you have to wait at least 40 to, if I'm not wrong, 45 minutes or something like that to activate the antennas and those other mechanical parts. But that's the whole point of deployer switches. You have to know that your CubeSat has been deployed. The firmware has to know that. So I have the provision for them. Basically, I've used two JST connectors. I can solder those buttons. Basically, the V3 load is what is being cut. So two in series, which means both of them have to be activated for the COMS3 V3 to have voltage. But I need to know when deployer switch 1 and deployer switch 1, 2, deployment switch 1 and deployment switch 2 are activated. So I sample that voltage using a simple voltage divider, and then I map it to 1.6 volts, basically to read from the by the MCU. So deployment switch 1 voltage is read by the MCU ADC, right here, switch 1 and switch 2. So these are very critical. They'll help you to know when the CubeSat has been deployed. I think I explained the remove before flight And yeah, I think that's all about this EPS. It's not very complicated. I have a simple buzzer just for testing, maybe on the ground in space. There's no one going to listen to a buzzer. So this is just for ground testing and diagnostics. Yeah, so that's that. A couple of test points. These are hookable test points. You can connect crocodile clips or meter probes that can hook to these test points just to verify that you are getting the right voltage levels. Yep. What else is there? Nothing. There's nothing much. So the only remaining thing on this board, rather on this design, is completion of this solar power bus monitor. I just need to feed the voltage here. Basically, I just feed this summed voltage, the voltage from this point. I'll feed that here. And then the other remaining thing is the MPPT. It's called MPPT, right? The maximum power point tracking for the solar panels, because they are very, very low efficiency. So I need to design an MPPT algorithm. First of all, I'll use the hardware. I'll use just an IC that has MPPT in it. But based on my research, I've realized that MPPT ICs are very expensive. They are somewhat very expensive. So I might just as well use as simple comparators and implement this whole thing in firmware, rather in the software side of things, to reduce the cost of the board. But yeah, that's it about EPS. 99% done, 1% is just this MPPT and layout. And yep, I think I'm certain this should work. This should work. I have a couple of things to fix. For example, these 5 volts. I don't know where it's going. It should go somewhere. I'll check that out. But yeah, this was the last board I was designing for this CubeSat. I think I am now done with all the designs. The others are done: comms, ADC, OBC, etc, etc. So they are done. Oh, one last thing I was mentioning was the load switch on the comms. So load switch on the comms has a delay of 265 microseconds also, right? And it's receiving 5 volts, right? So it means that, let me just say this, it means that if it's receiving 5 volts, there's a delay of 91 here, and there's a delay of what's it called, 265 here. So 265 plus 91, that's 350 something, 356, right? So 356 microseconds, that's enough time to wait uh, for before turning it on, before turning this regulator on and supplying power to the comms board components. Yeah, but now since this was about the EPS, that's it. And if you have any comment or question or correction, I know there's some things I might have missed, so I'm still reviewing the board, but let me know that in the comments and I'll appreciate. Thank you for watching and see you next time.